Okay, I think we can start with the continuation of our program. Hans-Peter Wieser, you will give the presentation, right? The range verification methods.
Yes, I think I just entered the Zoom meeting as a participant, so I cannot share my screen. So I will quickly go out and re-enter.
Yeah, just a second.
So I'm back.
You can try now to share.
Yeah. All right, can you see my screen?
Yes, very well.
All right, thank you, Jutta, for giving me the opportunity to present something on range verification methods. And basically, before I start, I also want to mention that please consider this as a complementary talk to what Professor Joao Seco was presenting earlier today about imaging, or basically anatomy tracking. My talk here is now about beam tracking, which is also important, but to really at the end guarantee a accurate and safe patient treatment, both anatomy and beam tracking needs to basically go together hand in hand, so that we at the end can really guarantee a safe treatment. So you always have to basically consider both. And so much to that. So now we talk about beam tracking and range verification methods. So I want to give a quick recap on range uncertainties. And what we see here is basically a one-dimensional spread out Bragg peak that's being delivered to this grayish area. That's our target tumor, so to say, where we want to deliver a high homogeneous dose of 3 gray. And when we deliver this individual pencil beams, we modulate them such that the superposition basically fulfills our clinical needs. And as we have learned previously, if during the treatment the protons penetrate out of a certain through different tissue densities, then we might over or undershoot the protons, which means that they stop at a more shallow or at a more deeper locations, which directly translates to an overdosage of healthy tissue that's surrounding the tumor and underdosing the tumor region. And the goal is to basically avoid this. And this is also here now highlighted. So such extreme over and undershoots for this one-dimensional homogeneous case is highlighted here for protons and carbon ions, just to give you a glimpse again on how range uncertainties impact dose distribution of charged particles. So the motivation behind range verification methods alongside anatomy tracking is really that if we have an accurate knowledge, or if we would have an accurate knowledge of the exact stopping location of ions inside our patient anatomy, then this would allow us to fully exploit the ballistic properties. So we could then fully exploit also the Bragg peak itself. And therefore, we would like to have also these in vivo range verification or treatment verification methods in charged particle therapy. And just to give you an overview, there are like four main methods on how to tackle this problem. The list is not complete, but these are the most prominent one, which is prompt gamma imaging, PET imaging, and also ion acoustics, and last but not least, MRI imaging. And I will talk about these four methods in the next 15 minutes or so. And what I directly want to point out that also in these range verification methods, also the time really matters, because all these processes happen on a different time scale. And so when we look at prompt gamma imaging, then this can be considered as real time, because the prompt gammas that we want to measure, it's basically far beyond the nanosecond range. So this is a real time beam tracking, so to say. The second approach is called PET imaging, positron emission tomography imaging. And this is delayed depending on the half-life times, and can also be used, or is mainly used for post-treatment verification. But there are also some developments in recent years to really do in-beam tracking of the particle beam. The third option is ion acoustics. So this is about acoustics. And here the readout is also delayed by the traveling time of the acoustic wave from the Bragg peak to the sensor that is typically being placed on the patient surface. But this is also, it's delayed, but it's in the order of microseconds. And last but not least, again, MRI imaging. Here, this is typically, or this imaging modality is also typically being used days or weeks after the irradiation. So yeah, this is basically just to point out that the 4 main methods I'm going to talk about, and also the respective timescales they're operating on. So what is the challenge actually when we want to do range verification? So here you see just a simple head case where the one proton pencil beam is coming in from the right side. It's a bit smeared out because of the heterogeneities. And now the question is, what is the range of this proton pencil beam inside this head? And this is not a trivial thing, because how do we measure a signal from the Bragg peak when basically all primary protons, they stop inside the patient? So this is also, please keep this in mind. This is vastly different to CT imaging or classical radiography, where you shoot in radiation from one side and measure the remaining intensity on the other side. This method cannot be applied here because, yeah, we want the protons to stop in our tumor, so they stop inside the patient, and we cannot use any direct protons for our range verification method. But what we can do is we can measure secondary signatures, I call them, also secondary radiation, but also secondary signatures, including acoustics. And another possibility is to correlate the physiological changes that have been caused by the stopping of protons inside the tissue to the proton range. And to directly tell you the impact, if we would have a perfect range verification system, then in principle, it would allow us to reduce the planning margins. So this is also something that Niklas mentioned today, that we have the clinical target volume, which is typically then being isotropically increased in all dimensions, and then we intentionally irradiate a larger volume just to be sure to give enough dose to the CTV. And if you could basically measure live in vivo the range of each pencil beam, then we could basically reduce this PTV margin. Another possibility could be that we could use new beam configurations or new beam directions. If you remember from the treatment planning sessions before, such a prostate cases typically being irradiated by 2 opposing proton beams. And maybe some other beam angle, as illustrated here with the blue arrows, would also be good to use, but are, as of now, clinically not being used because of range uncertainties and the critical organ at risk here, the distal fall off. So if we would know with high certainty where the protons stop, then could also allow us to use new beam configurations. It could also allow us to do more adaptive treatment strategies. And at the end, we can improve the patient treatment, because this is the main motivation, so to say. Okay, let's start with prompt gamma imaging. So the prompt gamma process is basically illustrated here on the lower right, where we have a proton from our treatment beam, which is hitting a oxygen nucleus, which is part of our tissue. And in this process, the nuclear interaction is happening. The proton is being deflected, and the oxygen is being pushed to an excited state. And after this, it de-excitates and sends out a prompt gamma. So, and this is happening on a very fast time scale, so far below nanoseconds. And this is the main process then being used for prompt gamma imaging. So we have this energetic prompt gamma emission from the excited target nuclei, which is mainly carbon, oxygen, or nitrogen. And this is basically when our treatment beam interacts with target tissue, then it comes to this effect. And basically after the excitation, there is this rapid, and that's why we call it prompt de-excitation. And what's also interesting to mention here, that the energy of the prompt gamma spans over several mega electron volts, which is then exponentially decreasing, and it also has some characteristic emission lines. And most importantly, the prompt gammas have enough energy to leave the patient, and we can place detectors outside and measure these prompt gammas. Another characteristic I want to mention here, that the emission of the prompt gammas is isotropic, which is also now then important to know in the next two slides. So in the end, we want to, so there are different kinds of informations that can be extracted from the prompt gammas. But most interesting is at the beginning the spatial location of the emission, because we want to know where it came from. Another aspect that's also important, or that can be exploited, is the temporal information. Can be used for noise reduction to basically filter out other secondary background radiation, but it can also be used to newer approaches or new developments that fall into the topic of prompt gamma timing. And the third point is also we can exploit the photon energy, because with that we can do spectroscopy, so we can measure the different discrete energy levels, or as I called it, the characteristic emission lines. And it also tells us something about the composition of the tissue we are radiating. So on my next slide, I'm showing you one publication that has been carried out by John Verburg and Joao Seco back then, a couple of years ago, at the MGH in Boston. And basically here on the lower left, you see the experimental setup. Yeah, this is an image of the experimental setup, and right next to it here, you see the schematic illustration. So the proton beam was entering from the left into a water or polyethylene target, and basically created prompt gammas. And then there was a tungsten collimator, which can, in first approximation, be just considered as a pinhole camera. And this is basically required to know the original location where it came from, because you only are sensitive to one direction, and then you can pinpoint down the original location from where the prompt gamma was originally emitted. And then there is also a detector setup and scintillator and photomultiplier tubes to then at the end measure the prompt gamma signal. And now I would like to draw your attention to this figure up here. This is basically the measurement that was performed, I think, like 10 centimeters upstream the proton beam of a 165 MeV proton beam. And on the left side here, you see the result of the prompt gamma energy. So basically the spectrum as a function of time for the water phantom, and here on the right side for the polyethylene phantom. And what you see here now are these discrete energy lines. And so what's important to mention is that these energy lines, they are different for the different targets. So the prompt gamma spectrum, therefore, depends on the tissue or the material we are irradiating. And here on the right side, you see now so to say, a scan parallel to the beam axis, where they introduce on the first measurement no additional material, but then on the second measurement, they added a 2.3 millimeter slab, which could then be successfully, but this shift of 2.3 millimeter could successfully be verified in this measurement. And here is a more extensive measurement about the different discrete energy levels of the prompt gamma emissions for the water and again for the polyethylene target. And here you basically see the results. Yes. One important thing I would like to mention here is that independent of what range verification method you use when you measure secondary signatures of the incoming protons, is how do you relate your signal to the Bragg peak? And this is one general problem that affects every method, but I will also come to that later on in more detail. So a more advanced setup of a prompt gamma camera can be seen here in this publication, where they were using a tungsten slit collimator. And the gamma camera had now multiple channels, which allowed them to basically resolve a one-dimensional prompt gamma profile in one measurement. And besides these mechanically collimated systems, there is also the possibility to do electronic collimation. So, but before I explain this, I would also like to mention that some of these collimated systems, they already reached clinical testing. So they have reached the clinics, whereas this the electronic collimation I'm showing here on the right is still under investigation. Many research groups are working on, but it still needs to be shown. And the idea here is that you exploit the kinematics of content scattering of the prompt gamma to then more accurately basically reconstruct the prompt gamma emission. And such a dedicated detector that needs to be developed that is comprised of different scatterers and absorbers could then in principle also allow for 3D imaging capabilities. And yeah, such a detector would also eliminate the use of a tungsten slit collimator. So moving on, the next range verification method that's also currently being investigated is positron emission tomography. And the idea here is that there are nuclear fragmentation reactions between the ions we shoot in and the transverse tissue. And this induces a radioactive beta plus decay, which is illustrated here on the lower right. So because of our incoming protons, a proton of a target nucleus turns into a neutron and basically shoots out a positron and a neutrino. And yes, this process is basically then the main that's the main process that's interesting for positron emission tomography. And what's also important to mention here is that each isotope basically has its own half-life time, and the half-life times, they vary strongly for different isotopes. So for nitrogen-12, it's 11 milliseconds, which could in principle allow in-beam tracking. But for carbon-11, the half-life times go up to 20 minutes until this beta plus decay is really happening. And at the end, we are also not measuring the positron, but let me start fresh. Once the positron is being emitted, it still can travel a couple of millimeters, and it will undergo Coulomb interactions with other atomic electrons until it's annihilated into 2 photons. That's being illustrated over here. And then we detect these 2 annihilated photons, which have exactly 511 keV. And another characteristic feature is that they are being sent out in opposite direction. And then we detect this signal, and this is at the end the positron emission tomography signal that we are detecting. One problem that we have here is that if we measure the 2 photons of 511 eV and do a reconstruction, then we basically reconstruct the location where the positron emitted, but it might not be the location where it originally came from. And this is basically also the problem I wanted to mention before, that it's always it's not straightforward to map the measured signal of a secondary radiation to the location of your Bragg peak. And to show you how such a system could look like, I want to show you this study where they were shooting in ion beams into this PMMA phantom. And basically the ring is now a positron emission tomography scanner. And here on the right side, you see the respective signals they could measure. And more interesting is the illustration down here, where you see in blue the Bragg peak, and then in black lines, in the black dashed lines, you see the PET activity or the PET signal. And this basically illustrates again what I was referring to before, that the peak of your, in this case, the PET signal, does not directly correspond to the peak of the Bragg peak or the range of protons. So there is always a so some sort of approximation that needs to be made, and this needs to be, or in other words, it needs to be quantified to do accurate range verification for protons. Now, I hope I still have 9 minutes, okay. So now I'll switch a bit to acoustics. This concept is a little bit different. And here the idea is that when a pulsed proton beam stops in matter, it leads to a local temperature increase, which then results in a thermal expansion, and it sends out an acoustic wave. And this acoustic wave can then be measured on the patient surface. And from the time of flight, so basically how long it takes for the acoustic wave to propagate from the Bragg peak, from its origin to the sensor, entails information about the location. And basically this concept is illustrated here. So if the Bragg peak for whatever reason is deposited somewhere else, then the thermal expansion is happening somewhere else, and this results in a time of flight offset. And by this we can also in principle detect different proton ranges. And this idea is not new, goes back quite far. In 1995, there was already a study where they successfully measured non-invasively a acoustic signal from a pulsed proton beam. And in recent years, this now found renewed interest. Yeah, I'm going to present now some results because I'm researching on this topic, and what you basically now see here is again the reaction chain. So we have the stopping of ions, it leads to a small local heating, which then leads to a thermal expansion and to a pressure wave, which then propagates omnidirectional throughout the patient. And what's also important to mention is when we look now here at the Bragg peak, there are different waves being emitted. So there is also an acoustic wave, a cylindrical wave being emitted from the entrance beam channel, and there is another wave being emitted from the Bragg peak itself, which is a almost spherical wave. And we are interested, of course, then to measure the spherical wave. And to show you how this could look like, here's an animation where the initial energy deposition of a Bragg peak is converted to pressure, and this pressure then propagates here in space, or in this case through water. And if we place a sensor here distal to the Bragg peak, that's highlighted here by the green cross, then we can record a wave, an acoustic wave, and basically can then relate back this peak and the travel time. We can then relate back where the protons must have been stopped. However, this is also very challenging because the pressure wave is very weak in the millipascal range and typically below 200 kilohertz. So in these areas, there is no sensing equipment. So just to keep in mind, if you use ultrasound, then you operate with kilo to megapascal pressures, and our pressure wave here is in the millipascal range. And how to basically jump back to the beginning, where I was mentioning that that anatomy tracking needs to be combined with beam tracking. A potential acoustic solution could look like this. So here we have a patient, an abdominal patient, and a small lesion inside here in the liver, which is now being irradiated from the top. And this basically leads then to an acoustic emission. And if we place a proper acoustic sensing equipment here distal to the beam, then we could measure the acoustic wave. And in addition, we could also measure with the ultrasound probe the anatomy of our patient. And this is basically here the image in the middle, which is the ultrasound image. where we see the lesion 3. And if we now measure the ion acoustic wave, which is basically illustrated here in the right figure, this is an acoustic simulation, we can then derive basically the location by simply taking the maximum, and this corresponds to a radius of response. And if we map this information back to our ultrasound image, then we can do, in principle, range verification on the underlying tissue anatomy. So much to that. And the last range verification method I want to mention is also MR imaging, which typically operates in days to weeks after the treatment. And here, the main idea is that MR imaging offers very good soft tissue contrast, and you can detect then these physiological changes and correlate them with the beam range. So you literally see a different contrast in your MR image that can be then correlated to the proton range. But this is mainly, as I've said, being used for post-treatment verification, but it was successfully used, for instance, in spine irradiation. And I would like to close my talk with one outline or one very preliminary study, but there are also colleagues in Dresden who are now also working on online MR imaging to verify the proton range. Exactly. So my conclusion. So non-invasively measuring the proton range online and in vivo is challenging. And the secondary signals, they can be correlated with the Bragg peak location, but this is not straightforward and it's not a trivial task. But the secondary signals, they are basically given by the prompt gammas, the positron emission tomography signal, or acoustic signal. And maybe also, who knows, MR imaging might be an alternative solution. And with that, I now reach the end of my talk.
Thanks very much. Thanks very much, Hans Peter. I think we should immediately pass now to the session of the students' presentations. We have only 1 hour, but it is the time that is dedicated to discussing the hands-on results. So I want to see if Silvia Molinelli is connected.
Yes, I'm here.
Great.